Very much. Let me first thank the organizers for giving me this wonderful opportunity and a big task of reviewing the whole supersymmetry in the last few years. So this is what happened a few months ago. This is really the excerpt from the email. I got an email from the elders of the string theory, the powers that be, saying that they would like to ask me to review the recent progress regarding exact results in supersymmetric H theories without any restriction, you see. So I asked them back, saying that, well, that's a very great honor. I try my best. But in which dimensions? With how many supersymmetries? I never heard from back. So I guess I'm forced to split my talk into 5 parts, covering d-dimensional SUSY theories for d equals 2, 3, 4, 5, and 6 in turn. Each will be about 10 minutes, further subdivided according to the number of supersymmetries. Of course, I'm joking. That would be too dull for you to listen to. So instead, I'm going to organize my talk around 3 overarching themes in the last few years. That is localization, non-Lagrangian theories, and multidimensional systems. Let me say a few words about each of these things. So localization allows us to compute partition functions exactly in many cases. And that gives us checks of all dualities. And it gave us refinements of those old dualities. And it allows us to study new dualities. Second point, non-Lagrangian theories. Well, those are the theories without no known Lagrangians, or with known Lagrangians, but that are not very useful. Still, we have learned how to use them quite a lot. Finally, mixed dimensional systems. That is not a word which is usually used, but I'd like to use this word to denote such activity as compactification of 6-dimensional 2,0 theory down to various lower dimensions. And also the fact that we started learning about not just operators supported on points on the space-time, but on loops or surfaces in the space-time. So these are the 3 topics which I think it was very huge in the last few years. Therefore, there will be 3 sections in my talk. The first is localization. The second is about non-Lagrangian theories. But the third is not about mixed dimensional theories, because that alone is such a huge topic. And I decided to talk really the mother of all of this mixed dimensional activity, which is the 6-dimensional 2,0 theory. So let me start by talking about the first point, the localization. So let me go back to history and point out 2 prototypical examples of localization. One is the topological quantum field theory of Edward Witten from 1988. There he considered 4-dimensional n equals 2 theories that have SO4 rotational symmetry plus SU2R symmetry in the supersymmetry algebra. He decided to redefine part of the Lorentz SU2R small r by a diagonal combination of SU2R and R symmetry in the supersymmetry algebra. So he took this as a new Lorentz symmetry. Then you can show that this gives you a covariantly constant spin on arbitrary manifold, allowing you to compute things exactly. The second prototypical example is this paper by Peston from 2007. There, slightly different method was used. So if you have, well, superconformal field theory, in this case it was 4-dimensional, again, n equals 2, that can be put on S4 by just a conformal mapping, because S4 is conformally flat. Of course, this can be done only for really superconformal theory, but guided by the Lagrangian you get by this operation, you can modify Lagrangians of arbitrarily 4D n equals 2 theories so that they have supersymmetries on S4. And again, that allowed us to do many things. In those days, these two methods look very different, but are they really different? No. So this was pointed out by these papers, and I'd like to say a few words about how this is done. So first of all, why can we put quantum field theory on a curved manifold? This is because quantum field theory has the energy momentum tensor T mu nu, and that knows how to couple to the metric. So here, by G mu nu, I'm not talking about dynamical gravity yet, but we can have non-trivial G mu nu background, and any QFT knows how to couple to that. If you not only consider QFT, but a supersymmetric one, that not only knows how to couple to the G mu nu by T mu nu, it also has a supersymmetric current S mu alpha, so it knows how to couple to the gravitino background. If this QFT has an R-symmetry current, it knows how to couple to R-symmetry gauge field background. Similarly, if the supersymmetry multiplet contains a scalar component, say XAB, where AB is the index for the R-symmetry, that can couple to a certain scalar component in the supergravity multiplet. Again, let me emphasize that these multiplets are there non-dynamically, so they are external fields, but you can consider various intricate configurations of them. So, Witten's original work used metric and the R-symmetry background, and Peston's work also uses this scalar background. So how does the localization work? Again, there's an analog in the ordinary QFT. So if you put a QFT on a non-trivial manifold with an isometry, in that case, if you take some operator and consider its variation under this isometry and take the expectation value, due to the rotational invariance of this manifold under isometry, the wave is 0. Exactly in the same way, if you have a supersymmetric QFT, and if you put that on some background which has a super-isometry or some killing spinor, then you can consider any operator and its supersymmetry variation, and the wave is 0. In the supersymmetric case, you can do a further trick. So let's take such an O that its second variation under this super-isometry is 0, and at the same time, this first variation is basically a square of the fermion variation. You add that to the Lagrangian with the coefficient t, then you can show that this addition doesn't destroy the supersymmetry of the theory itself, and you can also show that the variation of the partition function under the change in t is just given by the integral of this delta E of O, which I just showed you to be 0. This is invariant. Then by making t very, very big, you can localize the path integral to such configurations that, where delta psi is all 0. That space is usually parameterized by some space which can be disconnected, has many components, but usually each of the component is finite dimensional. So that I denote it as some direct sum of mi, then this partition function of the theory is a sum over the components, and for each component, you need to take the classical part of the action and one loop fluctuation, and you need to integrate that over this and sum over I. So this is the basic idea of localization. Every time this is the same procedure, but carrying this out in practice is rather complicated, but it has been done in various cases. So first of all, after the original work by Witten, there are many cases of topologically twisted theories worked out. Also, starting around 2000, there are so-called omega backgrounds where you use rotational symmetry of a non-compact space, and then Peston's work on S4 and other space-time in 4 dimensions, in 3D, 2D, or 5D in various cases, cases with boundaries, cases with codimension 2 operators. So many cases have been worked out. But let me emphasize that although I referred here just to the topology of the space-time, But in order to really put a supersymmetric theory and specify the partition function, you need to set all of the full supergravity background. But in the end, it is found that only the topological property of the square of this superisometry matters. Therefore, there are usually uncountably infinite numbers of choices of values of the supergravity background, giving you the same partition function. This is the reason why, originally, these topological twisted theories are called topological twisted, because it only depends on the differential structure on the manifold. And when Peston introduced his work, it looked like it only works on very round S4. But we now know that it's, again, almost like this topological twisted theory. You can have various supergravity background as long as you take the same superisometry Peston kept in S4. So it's very similar. There are so many great developments on localization in the last couple of years. And we've heard already a few about them in the last few days. So I'm not going to review these. There were various great talks in the parallel session, so some of you missed them, I'm afraid. So please watch the video. So instead, let me say a few words about localization of 5D theories, because it's not represented, I think, in the conference this year. And I think 5D localization has a bit of a slight conceptual twist compared to the other lower dimensional cases. So let me first recall that there are two types of supersymmetry multiplet, supersymmetry in 5 dimensions, minimal SUSY and maximal SUSY. Unfortunately, SUSY field theorists and supergravity theorists use different conventions. So very careful. So I guess many students are attending in this conference, so take note. This is one of the most important things in my slides. not get confused. So I will use just minimal SUSY and maximal SUSY in my talk. So there's a catch. 5-dimensional gauge theories are, as you know, all non-renormalizable. So it's not quite clear what we mean by doing an honest path integral computation on a given manifold, because there's no such thing as an honest computation in a non-renormalized theory in an exact sense. What do we mean by this? I don't have a satisfactory answer. One of my excuses is that it is often the case that we believe that there's a UV fixed point such that its mass deformation flows down to an IR-free gauge theory. And if we are computing some quantity which is RG invariant, we are just computing that well-defined quantity in its IR description. That's one excuse. Another excuse is that if all of the non-renormalizable terms are delta epsilon exact, then they shouldn't affect the localization computation. But I haven't showed that all non-renormalizable terms are delta epsilon exact. So the third excuse is that, again, somebody in the audience will seriously think about it and give us a resolution of this conundrum. But let's go ahead and compute. What do we see? So the kind of things we would see have been predicted in the last decade. So first note, in the 5 dimensions, this instanton density is a 4 form, and it's conserved topologically. So it's a conserved current. In the case of minimal SUSY, what typically happens, one prototypical case, is a superconformal field theory with exceptional symmetry group. And you can perform a mass deformation to flow down to, say, SU2 theory with a number of flavors with SO2NF symmetry. In this case, the inverse coupling constant of this SU2 is really the mass deformation. And the instanton charge here combines with this SO symmetry to give exceptional symmetry. In the case of maximal SUSY, you need to start from a CFT in 1 higher dimensions, and you can compactify that on S1. And compactification scale, again, gives you the coupling constant of the 5D Yang-Mills. In this case, the instanton charge is the KK charge. So this was predicted in the 90s. And now we have many non-trivial checks using localization and also topological vertex, which I say is a localization technique in the sense of string theory. And it heavily uses the instanton counting of Nekrasov because instanton current plays such an important role here. So there are so many works. I'm not going to read the names, I'm sorry. But there are work on S4 times S1, works on S5. And these days, there are very nice works on gauge theories on the Sasaki-Einstein manifolds. We used Sasaki-Einstein manifolds as a type 2B times Sasaki-Einstein manifold compactification in the past, but now we are putting gauge theory there. So as an example, you can start from 5D6 theory, and you can mass deform to get SU2 theory with 5 flavors. You also have a realization of it in the brane construction or in the Calabi-Yau compactification. And the partition function of this system on S1 times S4 is computable by gauge theory or refined topological string. Interesting thing is that in either of the realization where we can do the computation, not all of E6 symmetry is manifest. But after laboriously computing, you really see there's an E6 symmetry. So things work, and there are nice generalization to other gauge theories. 5D gauge theory has other applications. Some time ago, people pointed out that if you start from 6-dimensional theory on S4 times C and consider 4D theory obtained by reducing along C and consider its partition function S4, that's related to the 2D Toda theory on the Riemann surface. Yesterday, there was a nice talk in a parallel session by Cordova showing that if you first reduce along S1 in S4 and perform the localization here, you really get to the Toda theory. So this relation is now proved, derived honestly using this method. Similarly, if you put the same class S theory on S1 times S3, in this case, you have an honest S1. So you can just reduce along that direction and use localization here of the 5D theory and get to the QE deformed Yang-Mills. This relation was found originally by this collaboration. And finally, this, if you instead of put this on S3 times 3 manifold, again, you have some non-trivial 3-dimensional theory on S3, which should equal complex Chern-Simons on this X. And again, this was derived by reducing along S3. So I'd like to call this phenomenon a partial localization. So if you consider n-dimensional SUSY gauge theory on Sn, we get often matrix integral. But let's consider the matrix integral as 0-dimensional theory, right? So a generalization is that if you start from n-dimensional SUSY gauge theory and put on SD, where d is smaller than n, in general, we get n minus d-dimensional QFT. So this is the partial localization, and I gave you a few examples in the last few slides. I think this mysterious relation between the 6-dimensional 2,0 theory on S1 and 5-dimensional maximal supersymmetric Yang-Mills should be best viewed as an example of this partial localization, whatever that means. So that's my gut feeling. And as 2,0 theory is such a prominent example of non-Lagrangian theory, I'd like to move on to the next topic. A non-Lagrangian theory, for the purpose of my talk, is a theory such that the Lagrangian is not known or not agreed upon yet. So it's a time-dependent concept. Let me apologize. So maybe I should have called this a non-Lagrangian approach. Given a non-Lagrangian theory, there are two obvious approaches. The first approach, maybe a more honest approach, is to work very hard to find the Lagrangian. And the work paid off in the case of 3D maximally supersymmetric Chern-Simons theory, started by John Schwartz and BLG and AVJM. But there are some people who cannot wait, like me. So that's the second perspective. just work around the absence of Lagrangian and try to find some way to analyze it. So as I already said, six-dimensional theory is a prime example. I'll come back to that in the last section. But let me just talk about its compactification on a Riemann surface first. So this gives you 4D theory. And because we start from non-Lagrangian theory in 6D, you often get non-Lagrangian theory in 4D. This is called class S construction or tinker-toy construction, depending on the collaboration. I collaborated with both of these groups, so I don't know how to call them. So crucial idea by Davide e Gaiotto 5 years ago was that you can split the Riemann surface into components, into tubes here and spheres. Let me just talk about tubes first. In the original papers, they put some partial R symmetry twist on the original Riemann surface so that it preserves n equals to supersymmetry in 4 dimensions. In that construction, the tubes gave SUN n equals to vector multiplet because 6D theory on S1 is a 5D theory, and if you put that on a finite segment, you get 4D gauge field. So that was the original construction. But now, people generalized this to a R symmetry twist on the Riemann surface, which only preserves half of the supersymmetry, n equals 1 in 4 dimensions. In that case, again, you can still split the Riemann surface into parts. But if you do that, depending on how the curvature of this R symmetry twist is localized around the various tubes, you can either get n equals 1 or n equals 2 vector multiplet with SUN gauge group. So you can mix and match. So this allows you to have lots more 4-dimensional gauge theory engineered starting from the 6-dimensional theory. That's about tubes. Let me talk about spheres. So typically, you have 3 punctures. And associated to it is an SUN symmetry. So let's say A, I, U are each an index from 1 to n, so that SUN acts there. So this is some n equals 2 supersymmetric theory with this symmetry. T2, so n is the number of M5 branes we start with. T2 is, in fact, a Lagrangian theory of a very simple kind. It's just a free theory of hypermultiplets Q, AIU. So this is a tri-fundamental. The T3 theory is the E6 theory of Minahan-Nemetshansky. So it has E6 flavor symmetry. And in terms of SU3 subsymmetry of E6, the operators decompose as, again, tri-fundamentals. And also, you have some adjoint fields under each of the SUN. But not much was known in the case of general TN theory. So this was 5 years ago. 5 years later, thanks to the work which I already alluded to, which shows a relation of the superconformal index and the 2D Q deformed mills, we know the full BPS spectrum of operators of this TN theory. And guided by that, you can even work out what kind of chiral ring relations are there in the TN theory. So it's completely known. For general n, this is a superconformal theory, and at scaling dimension 2, for each SUN, there are adjoint fields. And you have a tri-fundamental, QAIU, with dimension n-1. You also have two-index antisymmetric tensor with dimension 2 times n-2, ... And you also have tri-k antisymmetric tensor representation with dimension k times n-k, up to the final one, which is tri-n-1 antisymmetric index tensor field. Of course, you can rewrite it as a tri-antifundamental, and you have the same dimension as this. So originally, we were wondering why we have this field and that field only, but we learned that there are so many fields in between. So we know this theory quite well, so much so that although this is a non-Lagrangian theory, we can analyze SUSY breaking in this system. So this is another chiral ring relation in this theory. I have told you that there are SUN adjoint for the first SUN and SUN adjoint for the second SUN, and the same for the third. And it's known that if you take kth power of those adjoint fields and take the trace, they become a same element as an element of chiral ring. So let's couple this Tn theory to one n equals 1 SUN vector multiplet, say to the index A. So index I and index U remain flavor indices. From the point of view of n equals 1 SUN gauge group, the matter content, this mysterious matter content Tn, contributes one loop beta function just as NC fundamental quarks would do. Therefore, you expect a deformation of moduli space, just as in the case of SQCD with NC equals NF flavors. And in fact, it happens. So one of these relations are modified so that flavor adjoint to the nth trace is different from another flavor adjoint to the nth power by this standard instanton factor. When capital N is 2, this just reproduces the well-known deformation of the moduli space of SU2 with 2 flavors, with n equals 1 supersymmetry. We can further add some gauge singlets, flavor adjoints, capital M, and introduce this coupling to small mu's, which are in the Tn theory. If you introduce these fields under superpotential, this forces you, this try to force you to have both adjoint fields to be 0. But as I already told you, there's this deformed chiral ring relation, which is incompatible with this constraint coming from the superpotential. So it breaks supersymmetry. And you can really check that there's no runaway, so it really does break supersymmetry. When capital N is 2, again, Tn theory is just a free chiral multiplet, and this really just the standard SUSY breaking mechanism of intrigator Thomas, Izawa, and Yanagida. And typically, in the 90s, there were many types of dualities and non-perturbative effects, which somehow only works for SU2 and SPN. But now we can generalize this to almost arbitrarily SUN by using Tn theory instead of the fundamentals. So that's the kind of thing you can do with the non-Lagrangian theory as one of the matter content. So my personal impression is that by allowing Tn and other various non-Lagrangian materials, we can have lots more fun in doing supersymmetric dynamics. And in the last few years, there are more and more non-Lagrangian building materials in 4D. So Tn and its variants, this was introduced from 2009, and they contain the Minahan-Nemeshansky's theories of E6, 7, and 8. We knew Argyres-Douglas theories from the 90s. Well, they are kind of Lagrangian because you start from Lagrangian SQCD with n equals 2 supersymmetry. You can go down to the phi r, but again, original Lagrangian is not very useful to analyze Argyres-Douglas theory, so I call it non-Lagrangian. But that's vastly generalized. And there's also theories constructed from Calabi-Yau labeled by 2 Dynkin diagrams, gamma and gamma prime, introduced by these guys. And also there are even more variety coming from Calabi-Yau DPG theories, introduced by these gentlemen. The known ones are mostly n equals 2. But we can mix it with n equals 1 gauge fields and the superpotential to have lots of interesting n equals 1 4-dimensional dynamics. There will be also genuinely n equals 1 supersymmetric non-Lagrangian materials too, I think, although so far we don't have any explicit example. So let me summarize this section by showing you big figures. So this was the kind of idea we had about supersymmetric theories maybe in the 90s. We love supersymmetric theories from those days, but we mostly thought just about Lagrangian theories. Then, well, there were stringy constructions, and now there are also holographic theories. We don't really know that every weakly curved gravity ADS theory corresponds to some Lagrangian theory, right? I mean, ADS 3 times S 3 times S 3 times S1. Maybe it's Lagrangian, maybe not. And in the last few years, 6D constructions are becoming popular. And I don't really know how to assign measures on the space, on the supersymmetric theories. And I'm not claiming that in each of the intersections, you really have an example. Some of the region might be empty, but we just don't know. But I think we have learned lots about supersymmetric theories that there are a lot more. There might be a lot more than just supersymmetric Lagrangian gauge theories. So let me compare this to some example you very well know. So two sphere, everybody knows, can be constructed in so many ways. It can be constructed as unit sphere in three-dimensional space, or by patching two coordinate patches around northern and southern hemispheres, or you can just introduce coordinates r and theta very explicitly and put some round metric, or you can start from two complex variables and take equivalence relation and get CP1. There are many ways. Each can give complementary info, but no one definition privileged. Just as the same way, I think, a single QFT can have various definitions or realizations. You can have Lagrangian gauge theory description 1. You can also have Lagrangian gauge theory description 2. This is usually called duality, right? And you can have also 6D construction or holographic construction or stringy construction. Each can give complementary info, but I don't think no one thing is privileged. We can use various constructions to learn about various aspects of it, just as we can learn about so much about S2 by using various different viewpoints. So that was what I wanted to say in this section. So let me move on to the six-dimensional 2,0 theory itself. Let me begin with the basics. So 2,0 theory in 6 dimensions, we have ADE classification. And I will only talk about SUN case. So this is very easy to understand. You put n M5 branes and if you start from n coincident M5 branes and decouple gravity, and you just take the interacting part. Suppose you put that on the torus. So please identify these edges and these edges. If you compactify first on this direction, you get 5D super Yang-Mills, maximally supersymmetric Yang-Mills on S1. And you can further reduce along this direction, and you get 4D SUN. With coupling constant given by the ratio of this LB and LA, where LB comes in the numerator, LA comes into the denominator. If you reverse the order, you get, again, 5D SUN and 4D SUN. But the coupling constant is the inverse of the first construction. This is the geometric interpretation from 6D of the S-duality of the 4D n equals 4 super Yang-Mills. So this is a very basic case. Let me talk about slightly more complicated example. Note that SUN theory has a Z2 symmetry, sending every n by n matrix to its transpose. I forgot the minus sign here, but there's this Z2 outer automorphism. Using this, you can put the 6D theory on a torus with a twist here, so that if you cross this line, if you go past this line, you have this Z2 symmetry. So let's analyze what happens. First, you compactify in this direction. You just get 5D SU2n Yang-Mills, because there's no structure along this direction. But if you go around this direction, you have this Z2 symmetry. Therefore, you end up with the invariant part of SU2n under this symmetry, which is USP2n. So you get USP2n gauge theory with this coupling constant. Therefore, if you take the S-dual, you have SO2n plus 1 gauge theory, with basically the inverse of the coupling constant. There is a factor of 2. Therefore, this means that if you first reduce along an S1 with Z2 twist, you have SO2n plus 1 gauge theory in 5 dimensions. This is a funny feature, so let me say it again. You start from 6-dimensional SU2n theory with Z2 symmetry, just taking transpose. If you just compactify that on S1, you get 5D SU2n theory, as many of you know. If you compactify that on S1 with Z2 twist, you get SO2n plus 1 theory. Note that SO2n plus 1 is not even a subalgebra of SU2n. So I'd like to say this. Have you written a paper, or are you reading a paper on the Lagrangian construction of 6-dimensional 2,0 theory? Please take your favorite one, put it on S1 with Z2 twist. First of all, your Lagrangian should have this obvious Z2 symmetry. Does your Lagrangian give SO2n plus 1 5-dimensional maximally supersymmetric Yang-Mills? This is a very good test whether one of your candidate 2,0 theory is really close to the true description of the 2,0 theory. So, if your Lagrangian passed this test, please tell me. I really like to use that in localization computation. So let's go on to another subtle feature of this theory. We know that if you are very careful, for the SUN theory with SUN gauge group is not SDO to itself. It's SDO to SUN over ZN. So where does this subtlety enters in this 6D construction? Are there 6D SUN, capital SUN and capital SUN over ZN? What is going on here? So the answer to this question comes from a subtlety of the 6-dimensional 2,0 theory that it doesn't have a unique partition function on a compact manifold. It only has a partition vector, and it's slightly outside of the concept of an ordinary QFT. This has been known for quite some time, but again, I don't think it's very well publicized, and I think this is a very important property of 2,0 theory. So I'd like to abuse my privilege of giving an overview of the recent development of the SUSY QFT and tell you about something that happened 5 years ago. So in the case of 4D SUN gauge theory without any, with only adjoint type matter field, if you put that on some manifold X, you can fix the magnetic flux when you perform the path integral. And in the case of SUN gauge theory, the magnetic flux are Zn valued. So you need to take a you need to specify Zn magnetic flux to each 2 cycle, which means that you need to pick a second cohomology valued in Zn. So this is small a, and you can consider the path integral with magnetic flux specified, let's call it Zx of a. Consider instead 6-dimensional 2,0 theory of type SUN on a 6D manifold M. Now you have something like non-abelian tensor field with 3-form field strength. So, and it's known that it has similar Zn flux, Zn valued flux with 3 antisymmetric index. So you need to pick an element from the third cohomology of the manifold valued in Zn so that its integral over any 3 cycle gives you the Zn valued magnetic flux. But due to the self-duality of the 6-dimensional theory, you cannot really do that if there are 2 intersecting 3 cycles, C and C prime, because in 6D theory, magnetic flux is mutually non-local with magnetic flux themselves. So instead, you need to do a bit more intricate construction. What you do is that you need to split this third cohomology into 2 parts of equal size so that no flux in capital A is mutually non-local to each other, and the same with B. So that's the decomposition you need to do. then you can specify a flux in this half or in the other half, but not both at the same time because they are mutually non-local. Correspondingly, you have partition functions labeled by fluxes in capital A or partition functions labeled by fluxes in capital B, but they are not independent. They are related by something like discrete Fourier transformation. This can be derived or argued in many ways, but I don't have time to talk about it today. So it can be phrased in a different way too. Instead of a partition function, we have a partition vector taking value in a finite dimensional vector space. That finite dimensional vector space has a basis labeled by half of the magnetic flux or labeled by the magnetic fluxes in the other half of the possibility, so that ZA is a component of this vector along this basis, and ZB is the component along the other basis. And these two bases have this nice inner product realized in the discrete Fourier transformation. So it's rather like conformal blocks of 2D CFTs. And theories that have partition vectors rather than partition functions are called under various names. Fried and Telemann calls it relative QFTs. Nati Zeibel call it meta theories. There's no fixed names yet, but there are such strange theories. And 2,0 theory is one of them. 6D theory of type SUN with n equals 2,0 supersymmetry, therefore, is slightly meta. It's not really a genuine QFT. So if you just put it on T2 without doing anything, it's still slightly meta. What you can do, for example, if you put if you put 6D theory in T2 times Y, is to utilize the structure of the T2 to make the theory non-meta and really genuine theory. So what you'd like to do is to decompose T2 into S1A times S1B, and using that, you can split H3, third degree cohomology of the total space, as 2 cycles in Y times S1A, or 2 cycles in Y times S1B. So that's the decomposition you can do using this decomposition. And when we define partition function, we just declare that we choose either this one or the other one. The subtlety is that this choice is independent of the order of the compactification. So you need to do similar choice when you go down to 4 dimensions, first compactifying on direction A and then compactify on direction B, or the other way around, or maybe compactifying along the diagonal, etc., etc. So you need to remember that this choice, this declaration, you need to make it less meta, is the thing you need to do in addition to the choice of the order of the compactification. That's the complication. And this choice picks up a particular genuine QFT in 4D by specifying particular gauge group SEN over ZK and discrete theta angles discussed in my paper from last year, written with Aharoni and Zeiberg. And the discrete Fourier transformation law I showed you in the previous slide reproduces the S-duality transformation law first found by Waffa and Witten in the case of n equals 4 super Yang Mills in 4 dimensions. So this analysis can be extended to all class S theories. So in this case, you have genus 2 Riemann surface. This consists of 2 TM theory coupled with 3 tubes. So in general, you have 2G copies of Tn and 3G copies of SEN vector multiplets. And you can work out possible choices of group structure you can put on SU capital N over 3G. So there are huge choices, because you can take some combination of subgroup of Zn to 3G. And you need to choose various discrete theta angles. And you can work out how they are acted on by the S-duality. So that's the thing you can do. So let's put then the 6D theory in some specific background, different from the n equals 4 setup. So let's put it on, say, S3 times S1 times C. In this case, if you consider the theory as a class S theory, obtained by putting 6D theory on C, the choice I mentioned here about various gauge groups, etc., just doesn't matter. Because space-time S3 times S1 doesn't have any 2-cycle. Therefore, you cannot put any magnetic flux there. So you don't have any. The choice doesn't have any effect. But still, as a 6-dimensional manifold, you see that H3 of M still has 2 non-trivial, 3-cycle coming from H3 of S3, and 3-cycle coming from S1 times C. So from the rule I described to you before, you need to, in order to consider partition function, you need to take the components of the partition vector, and that's labeled by either a magnetic flux here or magnetic flux there. Each of them is just a Zn group. Therefore, this means that you can either consider Za, where A is an element which is 0 to n minus 1, or Zb, where B is an element on the other side, which again is 0 to n minus 1. And they are really just related by the discrete Fourier transformation. I forgot the factor of 1 over capital N. But, so what are these additional labels, A and B? It means that for this class S theory, in fact, always has a Zn symmetry. Not very well publicized, but it's the case. So under one of the bases, the interpretation is Z with index A, which is from 0 to n minus 1, is the trace. It's a superconformal index, or the partition function on S1 times S3, restricted to a certain Zn charge, A. So that gives you additional label. Also, I alluded to this correspondence many times, but if you consider class S theory on S3 times S1, I told you that, and originally this was found by Gyade, Rastedi, and Yan, and I'm very sorry, I forgot. You're Azamat. I'm very sorry, Shulomo. By 4 nice guys. And, I'm very sorry. And they found that it's given by a partition function of Q-deformed SUN Yang-Mills on C. But the question is, which precise group structure you get, right? Capital SUN or capital SUN over Zn, or with some theta angle. So the answer is, by taking the Fourier transform of this side, you get the partition function of Q-deformed SUN Yang-Mills with whatever monopole flux you like on C. So that's the kind of thing you can find. So the final, his name comes up here. But, so final application, so the same subtlety appears at many places. So if you put 4D TN theory on S1, again, that's some kind of 3D theory. If you take the 3D mirror, it's known to become a rather nice Lagrangian theory, usually called star-shaped quivers or comet-shaped quivers. So at the central node, you have SUN, and you have SUN minus, UN minus 1, U3, U2, U1, and there are 3 of them. When n is capital 3, this is the compactification of E6 theory on S1, and this becomes the E6 thinking diagram. So a few years ago, with Francesco Benini and Dan Shi, we generalized the mirror of E6 theory to this general case, and we said that the central node is SUN, without specifying exactly what is the group. We found out, sorry, it's not we, but Razamut and Willett found out that it was a bit imprecise. So the correct correspondence for the 3D mirror is that if you have just Tn theory on this side, you have the central node is SUN over Zn. On the other hand, if you have Tn theory, which again, as I said before, has certain Zn global symmetry, coupled to dynamical Zn gauge field, which is, then you get the central node is SUN. So this can be seen by performing 3D localization on S3 or S1, S2 times S1 or things like that. So, this fact that the 6D theory is slightly meta and has some, it doesn't have partition function but only has partition vector is a subtlety, but it became relevant in the recent years because thanks to the development of the localization, we can compute very, very detailed structure of these theories. And these days, these very, very subtle distinction between gauge theories are now becoming important to really check the correspondences. So this is basically it. I have 5 minutes to go. Yeah, maybe I spoke too fast, but it's OK. So let me summarize. So localization technique has matured, and it gave us lots of checks of all the new dualities, which is great. So that was the first topic I discussed. The second topic I discussed was about non-Lagrangian theories. As I already apologized, this is a time-dependent concept. So it will have some satisfactory Lagrangian in the future. But if you cannot wait, you don't have to wait. There are many methods being developed by various people in our community so that we are now learning to analyze supersymmetric QFT in higher dimensions without Lagrangians. 6D, and the third topic was n equals 2 comma 0 theories in 6 dimensions. They are still mysterious. It doesn't have honest partition function, so it's not really a genuine QFT. It's slightly meta. So it has a partition vectors instead of partition functions. So this subtlety gives you many, again, subtleties in lower dimensions. But now you can really see these subtleties very directly using localization. So I would expect steady progress in the coming years in the supersymmetric gauge theory and non-Lagrangian theories in general in every dimension we can think of. So that's basically the end of my talk. But I have one more thing. I don't know if everybody can read this, but there was a certain paper that appeared in 15th of July, 1994. It's not quite exactly 20 years, but I think it counts as almost 20 years. So this is the famous paper of Seiberg and Witten, which made possible many of the subsequent developments of non-perturbative analysis of the supersymmetric theories in general. So I'd like to ask all of you, instead, to end this talk, instead of thanking me, but celebrating the 20th anniversary of the Seiberg and Witten theory and giving a big round of applause to Nati Zyberg and Edward Witten.
Thank you, Yuji, for a wonderful talk on advances. And it's time for a question.
So I have a question about the your arrows that you had going from 6 dimensions down to 5 to 4. Are they limits? Or are they equivalences? And in particular, I'm interested in compactification on the circle of the 6-dimensional theory. And if you said that the Kaluza-Klein modes could be interpreted as the instantons in the 5-dimensional theory.
That's right.
So are you suggesting that there's an exact quantum equivalence between a 6-dimensional theory on a circle and a 5-dimensional gauge theory? And if so, do you believe that the 5-dimensional gauge theory is a finite theory?
So there are many interpretations about this correspondence. I don't think the 5-dimensional theory itself, maximally supersymmetric Yang-Mills itself, is finite. In fact, there has been a paper by Douglas and the collaborators showing that there are certain divergences in the 5D maximally supersymmetric Yang-Mills. So we really need to be careful what we mean by the relation or equivalence between the 6D and 5D. So I think as far as the BPS quantities are concerned, every quantity in 6-dimensional theory on some manifold with S1 isometry will be captured by doing a localization computation in 5D with the matter content of maximally supersymmetric Yang-Mills theory. That, I think, will be true. But I don't think we can say anything about the exact equivalence of the 6D theory and 5D theory, because 5D theory itself, I don't think is a well-defined theory. So that's my interpretation.